Hello, it's Modern Retro, and today we are continuing this advent of code in Rust. We'll be reviewing days 14, 15, and solving day 16 live. So let's start with our review. I won't be reading the whole task descriptions for days 14 and 15, just quickly walk you through what we actually need to solve here. So day 14, we essentially need to do some bit manipulations. We get a program. Let me show you how it looks. Oops. Which has masks followed by commands for writing stuff in memory. So mask is zeros, ones, and x's, and memory commands are memory location address and some value. And then in part one, you essentially ask to process the value with the mask that is active at the current moment to change it before writing it down in memory. In essence, there are a number of rules for how you write the mask. So the program, blah, blah, blah. It masks value, essentially just override bits in the binary representation of the value. So if you have like 1 in the mask, output will always have 1 in this position. If you have 0 in the mask, output will always have 0 in that position. And if you have x, then position won't be changed in part 1 of the task. And that's pretty much it. You need to write stuff down, and then you need to calculate the sum of all the values in the memory. This is a bit similar to in-code puzzles and puzzles we had with also simulating computer this time. So, but it's not about some more complex programming. It's mostly about binary processing. I created an interface for that. So we have program, which essentially parses the input and creates a program instance. Then we have a method execute, and execution returns a computer state, and we can take memory from that, and then we can essentially take memory, which is just a hash map from addresses to values located in those addresses, goes through it and sums the values. So parsing part is pretty trivial. We use iterators again. We take input, we trim the ending, we split by new lines. And then for each line, we just split by this equal sign and spaces. And then we check the left-hand side, which can be either mask or memory with address part. And depending on that, we pre-process the right-hand side, or in case of the memory address, we also trim start and end to extract the address itself, and we save it. Our program is represented as a vector of instructions. Each instruction is an instance of a num. So we have set mask, which has mask, and we have write, which is a struct with address and value. Mask itself is also a struct. And here we have 3 representations of the same thing, essentially, right? We have the row strings that we got. We got ones. So this is the number you get if you create a binary number that contains all the ones from the mask, and all other numbers are 0. And zeros. And zeros are essentially inverted as far as I recall, because I put them. Let's quickly check the parsing logic. I did it 2 days ago, so I don't remember anymore. We take U64 from the radix, where we replaced everything except for zeros with ones. So that's the zeros mask. Then part 1 is solved quite simply. We essentially have this execute method that creates a new computer state, and then for each instruction, it either sets a new mask in this state, or it writes a value in address. And when it writes a value in address, it creates a new value using mask and calling a method apply on the mask instance. If you look at apply here, because of the representation I chose for the mask, it's quite simple to implement. We just have a bitwise AND operator working on zeros. So everything that we use AND with zeros will be 0, of course. So that's how we enforce that zeros are zeros. And we also have ones where we use OR operator. So that allows us to always set one where ones are set in the mask. And that gives us our result, the values that we actually need to write in memory. Yeah. One remaining thing that state is itself is just a hash map for memory, so mapping addresses to values. And it is an optional instance of mask because mask at first is not set. That solves the part one. So if we execute this, we get our result, and we get it very quickly. We get it in less than, well, okay, slightly more than half a millisecond, but I still think it's quite fast. And by the way, for converting to binary, what we use is this method from string radix, which allows us to take a string and convert it to binary or hexadecimal or any other radix, I think. I think it's not limited to, yeah, okay, to only binary stuff. Now, in part two, the logic changes. Instead of just writing down stuff, instead of just changing values according to the mask, what we do, we have memory address decoder, as they call it. So instead of changing values, we change addresses to which we write. And logic also changes. So if bit mask bit is 0, the corresponding memory address bit is unchanged. If the bit mask bit is 1, the corresponding memory address bit is overwritten with 1. And if the bit mask bit is x, the corresponding memory address bit is floating. And floating essentially is somewhat similar to non-deterministic Turing machine. Essentially, we need to consider both 0 and 1 for this position. And that allows us to write multiple values to multiple address locations at the same time. Here's the shown example how if you have those 2 x's, then you have 4 addresses to which you need to write. If you have 3 x's in your mask, then you have 8 addresses. So essentially 2 power of number of x's. And we need to execute the program with the new rules. So here are several things that we need to change, right? One thing is our execute thing is no longer valid. We need to, instead of changing value, change address. This is pretty trivial change, but we need to implement this decode memory address logic in our mask, and that's essentially the core of the algorithm. Now, sadly, compared to Elixir, Rust doesn't have good abstractions for working with binary data. So a lot of people rely on external crates. I didn't want to do that, and that's why I went with implementing logic based on chars, which is of course not a very efficient way of doing that, but it was sufficiently fast for my purposes here. So I convert this address, U64 number, to binary with just by formatting it as a binary string, essentially, with this syntax for formatting as binary. And then I go through chars iterator, I reverse it, and I enumerate it. I need to reverse it because my least significant bits are located here. There is also a concept of endianness, which is important for understanding that stuff, because you can put the least significant bit in binary number to the beginning or to the end of the corresponding bit strings that you write. And depends that you need to decode it differently. I always mix it up, so I usually test it and see if I got the number I expect or not. As far as I recall, big endian numbers are typically used when you send stuff over network, and little endian numbers are typically used for actual processing in the computer. But I may be wrong, and there are definitely some systems that don't follow this rule. Yeah, so we go through those characters in the address binary string, and we implement fault, where we just have a vector that we fill with possibilities that we will have. And we also use enumerate to get indices of the characters, which we use to shift stuff in the address. And then we do match. If we got 0 or 1, we know that we need to either set the bit to the stuff that we have in address at the corresponding or at the index that is shift, or we need to just always set 1 there. And if our possibilities is still empty, then we have only one possibility with this one bit that we just added. Otherwise, we map every possibility and we push this additional bit to all of them. If we got X, then if possibility is empty, we got two versions essentially. We got possibility 0 and possibility 1 that we will need to track. If not, we essentially go doing flat map on that possibilities vector. And for each possibility, we create two possibilities, in which case one has 0 at the new location and another has 1. And we then create a vector with those two things, and we flat map, so all the vectors get concatenated, so we get a big vector of possibilities after that. After we got our possibilities, we convert them to bit numbers, to normal numbers essentially, with this into iter and map, where we get each possibility is a vector of characters. We collect them to string, and then we use from string radix again to get the actual number for our address. That in essence returns us a vector of addresses. And now our execute method can take those addresses, and for each of those addresses, it just inserts a value. After that, the only thing that we need to do is, again, here we just call execute2 for the part 2, and we just go through memory and some stuff. So on my test input, we can see it takes significantly longer time, but still it's below 1 second, so quite fast. We get this value, which is the correct answer for me. So that was day 14. Now we should review day 15. So in case of day 15, we got a funnier problem to an extent. Elves want to play memory games with us, and this game is something that it's a sequence of a number that you build according to the rules they specify. It's known. After solving the task, I went to Advent of Code Reddit and I saw people posting a video from Numberphile about the sequence. I will post it later in the comments because it's quite fascinating. This sequence has a number of interesting properties, but not that much stuff is known about it yet. So there is no... Essentially, this is optimization task. There is no mathematical simple way to calculate the answer. You need to actually go through the steps. So I was actually expecting when I went to Advent of Code Reddit to find some magical solution, some formula for this, but it doesn't exist. It's really optimization task. Day 15 is all about doing stuff fast. So thankfully, I'm doing it in Rust. So that was a good match for this particular task. Here, memory game is pretty simple. You have a starting sequence of numbers. So in the sample input, it's 0, 3, and 6. And each number is spoken. So first they speak number 0, turn 1, somebody speaks 0, then another person speaks 3, and then another speaks 6. You get association between turn number and the number. And after that, you need to consider the number that was spoken last. And if it was spoken before, you need to take its previous two turns it was spoken and subtract one from another. So that's the difference that you then use as a new number in sequence, and you speak it. If it was not spoken before, you speak 0. And the task is just to calculate what number will be spoken on turn number 2020. Here, for example, you can see that they speak 0, 3, 6, and then 6 was not spoken before, so the new number is 0. In turn 5, the last number spoken was 0. It was spoken before, it was spoken in turns 1 and turn 4, so this number will be 4 minus 1, which is 3. And for turn 6, the number is 3. It was spoken before at turn 2, so 5 minus 2 equals 3 again, etc., etc. First, super simple approach that I took is just to take a vector of stuff. So I just split the input. I then just associated numbers with the turn numbers, and I selected my starting turn for my algorithm as the last turn, the spoken, that was in the starting sequence. Until turn is my expected last turn, right? So 2020 in the first part of the puzzle. And then essentially you take the vector, you enumerate it, you reverse the iterator, you filter, finding the positions where the last number was spoken. You have last number as a mutable variable essentially here. You take two last times it was spoken, you collect them into a vector, and then you match again using my favorite subslice matching syntax to, if it's empty, if it was not spoken before, if it only one time, well, it's the last number, so it was spoken only on last turn, so not before, then we speak 0. Otherwise, you get 2 entries for the last turn, of course, and for the previous mention of that number, you subtract one from another, convert to U64, and you push it into the numbers you have. In the end, the last number in your sequence will be the last number that was spoken. And for the first part of the puzzle, that worked fine, but for the second part of the puzzle, you need to say the number that will be spoken at 30 millionth turn. So vector with 30 million elements was a bit too large. And since my algorithm was quadratic, it was too slow. So I figured that I need to optimize. And here is essentially the essence of the task. How do you optimize it so that you don't need to wait too long for the 30 millionth turn calculation? In essence, I switched my data representation to be a hash map. Also, for clarity, I created a struct because at some point I was trying to modify hash map directly and I got all confused about, okay, where do I speak, which turn I'm in right now, etc., etc. So I decided to simplify it. And for that, I created the struct memory where we have number to turns, where we have a hash map. Now, you can see that this hash map signature is a bit weird because during my optimizations, I also switched to using build FNV hash function essentially, which you need to use this magical syntax to apply. That was pretty significant optimization. But before we go there, I think what we can do, we can just look at the previous version of this algorithm, right? So we got day 15, slightly faster. I think that was the actual revision I need, so I can just check it out and see. I can even go a bit before that because I think it will be interesting to see how it progressed over time. So oh, it seems I never actually committed the version without this 0 to turn optimization, but here you can see my first hash map attempt. So this thing has a hash map from U64, so the number of turn, to a tuple of 2 options. Those are turns that the number was spoken before. So the left one is the most recent one, and the right one is the one before that. And then I also implemented at some point, I figured that 0 is the number that's spoken more than other numbers in general. So I created a little optimization with 0 turns just put in this array of 2 elements. But that was not in my original version, and for now we can ignore it. In essence, actually we can even do stuff like that. We can just commit it out, and you can see that it will still work. Because when, so this stuff is all custom logic for 0. Yeah. So what happens then? When we go to last number spoken, we create this new memory struct. For now, it's without 0 to turns. And then for each turn in our input sequence we fold, we essentially create a tuple with turn and last number. And then from turn to till turn, so the out termination number of turns, we increment the turn number and we call memory recall. passing the less spoken number to it. Now, memory recall, it just takes the current memory reference and it looks at numbers to turn hash map. It gets this less number that was spoken. And if it was none, it returns a tuple of two nones because we don't have entries for that. If it was some, it just clones and returns the tuple that it's found in hash map. Now, depending on what it returns, if it was returning none, we know that we need to speak 0. If it returned only one instance of speaking before, we also know that it was just less turn, so we just return 0. If it has 2 entries, we know that it was spoken before, and we know that we need to do recent index minus pre-recent index and convert it to U64. Otherwise, it's impossible. We just fail. Well, that never actually get triggered, but Rust has no way of tracking this logic. And then we just call memory speak with the current turn number and the new number that we speak. And if we call turn speak, you can see that we have, we take this time mutable reference to the memory structure. We have turn number and we have the number that was spoken, and we just add a new record. Here you can see that we rotate the entries in the tuple. So we got this new number, and we only take the recent number from the hash map, and we put the new number in front and the older number in the back of the tuple. And then we just insert this in the hash map. So in the end, since we track in the last number, we know it, we return it, and that's our solution. Now let's compile this and see what our performance is like. And then we will go through the iterations of how I improved it over time. I hope that this still works. So if I execute it on day 15, you can see that this is super fast. This is day 15, right? Yeah, and my answer is correct. So number 441, it's less than 200 microseconds. Now, if I go day 15 too, it will take a couple of seconds to run. But at least with this implementation, you can see that it runs. So it runs in slightly more than 4 seconds here. We also got correct result for my puzzle input. Let's try to run it again to see if that number will be persistent. Yeah, it seems 4 seconds is the time it takes to run with this implementation. So now we can reintroduce our optimizations. So in this case, let's introduce this logic for 0 to turns. I think that's all. Yes. So here, since 0 is a number that is more often spoken, and then we need to update it also more often, I just extracted it from the hash map and put it into a separate array. And then in my logic, the external logic, of course, outside the struct memories implementations doesn't care about this stuff. But here I need to track it. So first I need to create this array and set it according to the initial input sequence. Then, of course, when I speak, if I speak number 0, I need, instead of updating hash map, to update this array. Well, that's also pretty typical swap 2 elements in array thing, right? And put another number here. So logic is the same as with hash map, but we just have like essentially static association between 0 and this array of 2 elements. And for recall, we also need to do similar stuff. Here, as you can see, it may be actually a bit more expensive because we are creating new structure completely. Still, let's recompile it and see how fast it will go with this optimization. I actually haven't tried it on this computer. I tried it on my laptop yesterday night, so I don't know if it will actually be faster, which will be interesting to see. Yeah, it is faster. It is really slightly faster. So that optimization worked. And as you can see, we are now below 4 seconds. So about, I would say, 200 to 300 milliseconds saved on that optimization. Now, another thing, of course, was to make that go faster still. So let's go to this version. You can see that one thing that I did, I changed from having this tuple of 2 options to having just a tuple of 2 usize variables. Why? Well, this is because of ownership. So in Rust, options they own the values they have, and they are non-copy, which means you need to clone them, which means you have additional price for needing to have this structure and copy it around. usize is a copy type, and when you use it, it will create, you don't need to copy anything, you can just pass it around. It's just an integer that fits into the memory of 64-bit computer. So using a tuple of two numbers, I believe, is more efficient. And it also simplifies the code. I still need to somehow represent my logic about turns, but here we get a little bit of help from our task definition, because you can notice that the first turn is turn 1, not 0. So we know that 0 is essentially none in this turns map. Same, of course, for the array that we use for zero optimization, right? Otherwise, the logic is exactly the same. We just have usize now. So here, for example, we return usize. You can see that it became way more, how to say it, compact, because we now can just access this stuff and create a tuple. It's only like one line. And in general, code, funny enough, looks cleaner with this stuff. I know that this is, like, in principle, it's more maybe correct to have option, but in this particular case, I think it's actually a better solution. So now, if we execute cargo run release, it will take a second to compile. And then we can do day 15 part 2 and see how fast it will go now. So you see, we got slight improvement, very, very slight. It's also like 200 milliseconds in the best case scenario, but we are getting there. Like, if you calculate the improvements we got so far, we're already almost half a second better. And that was without like super major refactorings. You can see we started with this, we started actually with non-terminating programs. So with Vector, it never even terminated because it was too slow and it required too much memory. This hash map, it became a program that terminates in about slightly more than 4 seconds. Then it's slightly above 3.8. Now it's between 3.55 to 3.7. So we are getting there. Now, after that, and that was not my idea, I actually went to vet of code because at this point I thought, okay, maybe there is even better way to optimize that. And one thing that I found is first, nope, you actually need to calculate stuff. So you only have very like low-tech solutions now, from now on. And I also found a post from another person saying that in Rust, they used another hash function. So I decided to try it. And so far, that was really cool. So let me go back to master. You can see that I got those FNV hash stuff happening. And I can now do another cargo run release. So what is the deal with FNV hash? This is a crate, and I will show it to you quickly. It's a crate that provides you alternative hash function for a hash map. Hash map, as obvious from the name, uses hash functions to figure out where items are actually stored in the arrays it uses internally. And the default hash that Rust uses has a number of properties. It's sufficiently fast. It's also sufficiently stable for hash DDoS attacks. So sometimes you can bring stuff down if you have a hash map there, because hash computations are usually a bit more expensive. So if you add a lot of stuff very quickly, it can break the service. In this case, they have specific mitigation for that in that hash function. So overall, it's a good round-the-block hash function. You don't need to do this kind of stuff with programs most of the time. But here, we have very particular use case, and we need to hash a lot of very small values. And for very small values, for like U64 or I64 values, the default hash that Rust uses is not optimal. Mostly in hash maps, you use something like strings. In this case, you really can benefit from a hash function that specifically works better for smaller values and is faster. FNV is one of those functions. So also if you look at the repos, they talk about that, that it's demonstrably faster. I believe they have some You can see that they have some benchmarks. So I believe SIP is the function that Rust uses by default. FinV is blue, SIP is red. And here you can see that depending on what you're doing, you can choose different hash functions. So try FinV hash. And now when we run this part, you can see that we became significantly faster. So now we are running slightly above 2.5 seconds. On my laptop, it actually runs in 1.8 seconds because it's significantly newer than my iMac from which I'm streaming. But you can see that this is way more acceptable timing. And it's almost, I would say, 30–40% improvement. So quite nice, I would say. Now, that concludes the day 15 review. And now we will start with actually solving day 16. But first, of course, as usual, we can use our magical REPL interface and create the next instances for files and for input that we will need for day 16. Which it did. And we can now read the task. I read the first part before. Break the server, yeah. Definitely. So day 16, ticket translation. I read the task before. It's I'm quite excited about this one because it looks like the part 2 will be about constraint satisfaction, but we'll see. I don't know what part 2 will be because I didn't want to spoil the solution for myself. So I only read part 1. But I will read it now for you. Day 16, ticket translation. As you walk into yet another connecting flight, you realize that one of the legs of your rerouted trip coming up is on a high-speed train. However, the train ticket you were given is in a language you don't understand. You should probably figure out what it says before you get to the train station after the next flight. Unfortunately, you can't actually read the words on the ticket. You can, however, read the numbers, and so you figure out the fields these tickets must have and the valid ranges for values in those fields. You collect the rules for ticket fields, the numbers on your ticket, and the numbers on other nearby tickets for the same train service via the airport security cameras. Together into a single document, you can reference your puzzle input. The rules for ticket fields specify a list of fields that exist somewhere on the ticket and the valid ranges of values for each field. For example, a rule like class 1 to 3 or 5 to 7 means that one of the fields in every ticket is named class and can be any value in the range 1 to 3 or 5 to 7, inclusive, such that 3 and 5 are both valid in this field, but 4 is not. Each ticket is represented by a single line of comma-separated values. The values are the numbers on the ticket in the order they appear. Every ticket has the same format. For example, consider this ticket, blah, 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 101, blah, 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 102. You got the picture. Here, question mark represents text in a language you don't understand. The ticket might be represented as 101, 102, 103, blah, blah, blah numbers. Of course, the actual train ticket you're looking at are much more complicated. In any case, you've extracted just the numbers in such a way that the first number is always the same specific field, the second number is always a different specific field, and so on. You just don't know what each position actually means. Okay, so each index will correspond to specific field, which is very important, I guess, for the part 2, I would imagine. Start by determining which tickets are completely invalid. These are tickets that contain values which aren't valid for any field. Ignore your ticket for now. For example, suppose you have the following nodes: class 1 to 3 or 5 to 7, row 6 to 11 or 33 to 44, seat 1340 or 45 to 50, your ticket 7114. So looks already impossible too, but okay. No, actually it's possible. It's possible if this is row, if this is class, and if this is seat. Okay. Nearby tickets 7347, 40, 450. So 4 is outside of our ranges. 55, 2, and 20. 55 is outside of our ranges. 38, 6, and 12. 12 is outside of our ranges. It doesn't matter which position corresponds to which field. You can identify invalid nearby tickets by considering only whether tickets contain values that are not valid for any field. In this example, the values on the first nearby ticket are all valid for at least one field. This is not true of the other 3 nearby tickets. The values 4, 55, and 12 are not valid for any field. Ooh, there is a mistake in the task description. Adding together all of the individual values produces your ticket scanning error rate, 4 plus 55 plus 12, 71. So we need to extract the invalid values. Consider the validity of the nearby tickets you scanned. What is your ticket scanning error rate? Okay, so get your puzzle input, sure. Oh wow, that looks really interesting. So nearby tickets. So each ticket is like this line of numbers. And then we got your ticket, and then we got all the fields. So we have 20 possible fields. Pretty cool. The format at least is comparatively easy to parse. But as usual, let's start parsing stuff. Parsing stuff is hard. Another possibility, of course, that this might be some kind of interval magic, which will be a bit less fortunate, but let's try it out. So we probably need to represent this stuff, right? So we will have rules where we will have, I will just say fields, and it will be a hash map with, because I don't know, maybe the second part will ask me to actually figure out which field is which on which ticket. That's also possible. And then I will have ranges, right? So actually, I wonder if I can use standard Rust stuff. So does it have something like range? Let's look. Because I think it has those things. Open, inclusively below and exclusively above. Ooh, range inclusive. That's what we need, right? Below, oops. A range bounded inclusively below or above start and end. The range inclusive start contains all values with x and x. It is simply empty unless the iterator is fused, but the specific values of start and end after iteration has finished are unspecified. Other than this is empty will return true once no more values will be produced. 1, 2. Okay, and then we have methods like contains. Oh, that's actually really nice, because then we can just check stuff. We will have nice syntax, and we will be able to check containment here. So this is standard ops range inclusive. Neat. Learning some new Rust as well. I didn't. I think I saw it in somebody else's code some day back. I think it was in some article I read about Rust, but I never actually used this stuff. Yeah, and this is just a normal struct, so range inclusive. I guess this will be then. Those are all positive. I will say U64, U64. And yeah, of course, we also will need use standard collections hash map. I guess we can even do it like that. So using tuple struct. And then, oh yeah, of course it should be only one now. Makes sense. You cannot mix two types in one range, right? And then we will have a ticket, which will be just a vector of U64. I'm using U64 for simplicity because I don't want to do all the conversions between U32 and U64. So of course it is, you don't need to use U64. I think, well, you cannot use U8 either, but I guess you got the idea. Yeah, you cannot use U8 here. Then what do we do? I actually think in this case, function parse will be independent from those structs because I have both rules and ticket in my cation, right? So I will get, oh, actually, let me model the whole task. So struct task will contain a number of things. So it will have those two, and it will have rules, which will be rules. Actually, that's, I guess, what I need. I don't need a separate struct. It will have ticket, which will be ticket. In this case, I may need to implement some logic differently on each of those. So, and your ticket, and then tickets, which will be a vector of ticket, right? And here then I can do task. I can do parse, which accepts input, which is a string, and then it will return a task. And just for simplicity, let's do it like that. Then, of course, I have a number of things here, right? So I always want to be able to see what I'm doing. So debug, I want to clone stuff. I probably want to be able to compare quality for my tests. So those are traits that I derive. And then we get our input. So we remove the terminal white space, we split. And then let's do it a bit differently this time. So I wonder if I collect it to a vector, and then I will try to pop stuff. So remove the last element. So I will reverse it, and I will do this, because then I can do it this way. I can do hash map for rules. So let's go for a completely imperative solution this time. I usually do like fold and stuff. I think let's try something else. Yeah, I will do to do so that it doesn't annoy me with the error here, that I'm not returning what it expects me to. And then while line is not equal to an empty line containing actually just empty line, right? And this also is mutable. So everything is mutable this time. So while line is not equal to empty line, why don't you like it? Because lines pop is, I will be brutal and just do unwrap, of course, here, because I know that this will be all right. I will have my field separated by this, and then I will get those two numbers, right? So I will just be looking at this rule so that I know what I'm parsing. So we split it by this, and we collect it to a vector, and then we match it. Actually, I can even do better, I guess. I can do if let, and then I can do what do I have? I have field name, and I got ranges, right? And this will be, I got split, I got collect, and here I need to use my magical sub-slice pattern. I wonder if it will work. I guess so. And here, of course, it will be equal, right? And this will be reference. Can I do this? Oh, okay. So that's nice. Then rule, I can take ranges. And ranges, I need to split again. So ranges will contain this stuff. Actually, we'll have two, right? We'll have this and this. where we will have, or even we can we do array with those? Not sure. Oh yeah, we can. Okay, that's nice. So we are going for more imperative solution for now. We're splitting it with or, and we're doing the same thing, right? We're doing range 1, range 2. We also convert it to a slice, right? Okay, splendid. And then we need to extract the numbers from ranges, right? So I will create a small helper function here, saying parse range, that will take the range as a stringlet thingy, and then it will return range inclusive u64. And here, so this part we need to parse. We do again split. We do we split this time on dash. Yes. And then we can do again the same trick. Actually, I don't know how efficient it is to do it like that. If you have a clue, if this is actually efficient way of converting to slice and then using sub-slice matching, do write in the chat or in the comments. But I definitely know that this is probably the nicest way I know in Rust to write this kind of stuff. So yeah, I will just match in this case because, and say start end. So start parse u64 unwrap. Let end and parse. You can notice that I'm using unwraps, though I'm also modeling my domain. It may look a bit weird, like why do I care? Well, modeling the main helps me to maintain this stuff and extend it to part 2, typically. Processing errors, not so much, because I have many tests for this stuff and I execute it all the time, so the tests are quite contained. Of course, in production code, you should never use unwrap, but that's not production code, that's advent of code, so. I also try to improve my skills of modeling stuff in Rust, so I think those tasks are really cool because they have 2 parts, and second part, you don't know what will happen, so it's kind of like you need to guess the requirements. Yeah, and then start. This is the syntax, right? Actually, unexpected input. So sure. Well, we can take range. Okay, interesting. It seems that this works. So then we can say right, and then we can do range 2. And here, I believe we have everything we need to do, right? We can then take rules and we can insert, and our key will be field name, and our values will be an array of range 1 and range 2. Okay. Then, of course, oh yeah, and one thing, we need to change our line. So line will now be rules pop. Or lines pop, of course. Lines pop unwrap even. So that already should give us idea about rules. Let's try to see what our test will say. We just debug printing to see if we are correct so far. Did it even? Oh yeah, of course our solver doesn't call it yet. So let task equals to task parse input. That's magical incantation we need to pass here, and then we can try to do this. It should fail in the end because we have to do, right? But we should get our ranges. So let's check. So arrival station is 27 to 809 and 834 to 960. Class is 34, 6, blah, blah, blah. Okay, it looks correct. And the last one was zone. Zone we also have. Okay, splendid. So next thing we got is your ticket. So we just do lines pop. The next thing is, and actually we can also even do an assertion here, right? So this stuff should be equal to, talking about failing fast, to this. And of course, yes, unwrap, please. Okay, and then this comment is also not needed, which is nice. Then we got our ticket. Let's also extract function for parsing ticket. So we have parse range, and we will have parse ticket, which takes ticket, which is also a string slice, and it returns ticket. Oh, actually, what am I doing? I can just create an instance method on ticket struct. So parse input string. That we don't need for now. It returns ticket, and here input, just in case, splitting by comma, I think. Is it comma? It's comma. And then we got, and then we just collect into a vector. Oh, and of course we also need to map this beauty into numbers. So value parse u64 unwrap collect, and that is our ticket, and we need to just wrap it into ticket. We can implement from and stuff, but I don't want to do it because yeah, well, it doesn't improve our domain model much, and it will be additional time spent on stuff that is not related to task. So we do this, and then what we do, so we got rules, then we got your ticket, which will be lines pop unwrap, and we just do ticket parse. Then we do more popping. This time we say nearby tickets. And yeah, they're exactly the same, right? So we just go and say, let's create, it's called tickets, yes. So we create an empty vector, mutable empty vector, and then we'd say, while let ticket equal to lines pop, and here, of course, sum. So here we are just pattern matching until we have lines where let ticket will be ticket parse ticket line And actually I can also just call it line, because at this point it's just a line. So we got a ticket, and then we just tickets push into the lines. Ticket, of course. And in the end, the only thing that we need to do, we take task, we say rules, your ticket, tickets. Order doesn't matter, but I try to keep it consistent for simplicity. What doesn't it like? It expects, of course, we need to have strings here. So this we can convert to string. And our parsing seems to be complete. We can put debug here now, and we can run it to see if we got everything correctly. Does it do it? Oh, we failed with nearby tickets. Why? Line pop. Oh yeah, because we need to do another line pop, right? So lines pop, because we have an empty line separating those. So we do pop unwrap. It will be an empty line. And then we can run it. So we got a bunch of things here, right? Our last ticket from nearby tickets is this. Looks correct. So this is just a vector of all the tickets we've got. And then eventually, oh God. I think I ran out of space in my terminal. Can we do, let's instead do your ticket as well, to make sure that this was parsed correctly. So 101 to 131. Yup, checks out. Okay, we finished with parsing. Now we need to actually solve the stuff. And as usual, I guess it will be significantly simpler than parsing things. So we got this task. And then what do we need? We need to, whereas it has nearby are not valid. Adding together all of the invalid values. So we need to get all invalid values on the nearby tickets. For now, we just don't do anything with our ticket. Do we have a nice place to put those nearby values logic there? So values, tickets. Let's say, let's create a function here. So invalid values, where we just take a reference to self and we return a vector of those things, which will be U64s. So for each ticket, well, let's keep this imperative stuff for this task for now, at least. Maybe second part we will need to write a bit more functionally. We will see. So let's say values, that will be a vector again. Tickets for ticket in tickets iter, right? And then ticket for value in ticket iter. Ticket is ticket. Well, I'm going inside it, which is not a really good thing, but for now I think it will be all right. We can move this logic later in the ticket itself. Because actually, self rules. Okay, for now let's keep it here because I don't know, I may need to optimize this. And if value, so, and then we need to go through all rules and see if everything corresponds, right? So, oh, that will be another function here. Value matches some rule. In essence, we will get value, and we get also reference to self. And then for self rules, so for rule in rules, if rule rules, okay, this is field name. We actually can match it. So rule 1, rule 2, right? If rule 1, is it, yeah, it's reference to inclusive range. Contains is the method that we need. Contains value. Return true, right? If rule 2 contains value, return true. Otherwise, return, well, we don't need to return, we just do false. It doesn't like it because expected reference, sure. Actually, we can even accept reference here, right? Because we probably will get them there anyways. And for each value, we just say if value, if self value matches some rule value, if doesn't match some rules, then we say invalid values push the referenced value. And then we return invalid values. I must admit, it probably would have been slightly more beautiful with functional style, but I think that's also quite easy to read. So we got invalid values, and then our task 1 will be just get that invalid values, and then we just into iter and sum. And this, by the way, will be U64, right? Ticket scanning error rate is this number, and we return some box new ticket scanning error rate. So that's our part 1. Let's take the sample inputs that we got here and test if we solve the task correctly. So we got this. I can copy this logic here. And what we should get some box new, which should be 71 in this particular task. So let's see. Yep. So then let's use our fancy REPL interface. And we got this value. Yeah, we solved part 1 of day 16. Quickly adding it to our test before reading part 2. Okay, splendid. Continue to part 2. Let's continue to part 2. Now that you've identified which tickets contain invalid values, discard those tickets entirely. Use the remaining valid tickets to determine which field is which. using the valid ranges for each field, determine what order the fields appear on the tickets. The order is consistent between all tickets. If seed is the third field, it is the third field on every ticket, including your ticket. For example, suppose you have the following nodes based on the nearby tickets in the above example. So if I try to solve it by hand, you can see 11, 12, and 13. So 11 matches to this rule, or this rule. 12 is this, or this, and 13 is this, or this. So by one, like every of those numbers can be any field, but then you can have other things. So here we have 3, which can be either class or row. So we know that this is only class or row. Then 9 can be row, class, or seed. 18 can be anything too. So we just know the class row is this. Then 15 is both in class row, but 5 is only in class. Oh no, actually it's also in class or row. 1 is in all of them. 5 is in all of them. Yes. Yeah. 14. 14 is not a seed. Class row not seed. So this is probably seed. And then this is, let's see. Seed is 13. Okay, I got it. Row is 11 and class is okay. So that's how I essentially just ran AC3 algorithm on that in my head, which allowed me to almost solve it, but we will solve it with backtracking. Now, this is super exciting stuff for me because my channel started with backtracking and AC3 algorithms in Elixir. Those problems are known as constraint satisfaction problems. I will also link those videos in the comments and in the video description, so you can check it out if you want to understand algorithms better. But I will quickly run you through the backtracking algorithm I will be using now, because then it will make way more sense what I'm doing. So in backtracking, you start with your constraint satisfaction problem definition, which essentially, let me find a good example of how to define it, which has variables, which has domains and constraints. Variables are just some assignment of variables you have. In this case, it will be fields, right? And domains will be the indexes. So like where the field is located in this vector of field values for a ticket. Constraints then will be constraints that we have here. So in this case, our constraints will be those rules, so like inclusive ranges. Now, once you have that, you can use the same algorithm to solve any task of that class. And one of those algorithms is backtracking. So you start with an empty assignment of values. I wonder if I can make it slightly, but not super large. Oh, that's perfect. So we have an assignment, the current assignment, we have a list of unassigned variables, and we have the CSP struct. And then we take the first unassigned variable, we fetch domain for that, and for each value in this domain, we try to add this to our assignment. So then we check if our constraint satisfaction problem is still consistent. And if it is, we just call ourselves recursively with the rest of unassigned values. Once we arrive at a solution, we will have no more unassigned values and we can return it. If we encountered a contradiction, we try another value, or we return from our function if we didn't find anything. And that's how you eventually find the solution. So let's try to implement that. This time in Rust. Of course, I also have a little Elixir library for solving constraint satisfaction problems. So it would have been super neat if I was solving everything in Elixir, because I could have just called my own library for this task. But let's try to solve it this way in Rust. So We will need to move this logic actually to ticket, right? Because we will need to check if it is valid. So we take a reference to self. And we take a reference to task. Actually, no, that should be still method on the task. So we say, because we need to implement that because we need to exclude invalid tickets, otherwise we will be screwed with our assignments. Ticket. We will return false. True. Otherwise, we'll return true. And then we can create a function that gives us only valid tickets, right? Let's return it as only thing. I don't care about copying because we don't have that many, right? Here, so we create a copied iterator and then we just do filter, ticket, and then we collect. Oh, cloned, I guess. Yes. So we copy everything then, and we collect it into a vector of valid tickets. We can already also start writing stuff here. Right? Is it the same input? It's a different input. For now, I will comment it out, and I will take this. Sample 16.2, and I will copy this stuff. And then I will call solve2, and for now it will return none. Let's run it. Got 3 valid tickets, which is true. They are all valid. Based on the nearby tickets in the above examples, the first position must be, yeah, once you work out which field is which, look for the 6 fields on your tickets that start with the word departure. What do you get if you multiply those 6 valid tickets? Oh, okay, I see. Because I actually figured that I forgot to read what we need to output. But that's fine, I guess. So, and now what do we need to figure out? We got valid tickets, we need to figure out the value assignment. So for that, we will need to do backtracking. I will not try to model the backtracking generically as I did in my Elixir videos. Consider it to be an exercise for a reader. I think I did it already in Rust, and it probably is even on my GitHub. I will look it up. If it is there, I will put a link in the description so you can see how you can do it generally. But for now, I will just go with the custom backtracking implementation here. So field position to index. So this thing will accept a value to self, and it will only take tickets, vector ticket, and reference actually to the ticket vector. And then what else? What will be our assignment? Our assignment will be hash map from string to usize. So from the field name to the position. So that will be assignment. Let's call it like that, so it's a bit simpler to work with. And then we will have assignment, and we will have actually at first we will have nothing here. This will be just our function. Then we will have field, oh, of course, field to index inner, and that one will have tickets, assignment, and unassigned, which will be a vector of strings. Yes, and it will also return assignment, right? So to index inner, we call this self, we call this tickets, we call this assignment. At first will be hash map new empty. Unassigned will be everything essentially. So it will be rules, keys, self, rules, keys, cloned, collect. Of course, we call it on self. I'm dumb. This is still inside. That's our starting position for backtracking. We don't have anything there yet. Now, what we need to take, we just need to take the first unassigned value, or more precisely, we need to see. So if unassigned is empty, we know that we solved the task, so we just return assignment. So that's our terminal case of the recursion here. Let me make it a bit bigger as well so it matches fully. So alternatively, we take the first unassigned value. So we take assigned the value to assign, which in this case will be actually field to assign, right? And it will be and the new unassigned. Let's for now return. Make sure that we return of the same type here, which will be unassigned pop, I guess. Can we do that? Yeah, I guess. Well, no, it's not mutable. We will need to do it like that. We need to say unassigned. And then here we can do, I'm creating a mutable thing here, right? Local variable. Then I create unassigned, I pop. That is this. And my unassigned is now also changed, right? So I can then use as a vector here. Then we need to go through each value that is valid assignment, like through each index that we can assign here. And we cannot, of course, use the indices we already have in our assignment, right? So, and we only can use indices that are inside our lengths of our rules, right? So, thinking ticket lengths. So I will just say max length, max index, which will be then so that's our, actually I can just keep it at lengths. Let's call it ticket lengths for simplicity. Ticket length, I can pass it around. Which will be usize, yes. And then for 0 to ticket length, for ID index in, of course we need to do ticket lengths here as well. What don't you like? Oh yeah, of course. So if assignment values contains, what is that? So let's say assigned indexes, which will be this. Let's collect it to vector, right? And those will be, yeah, references to usize. So I think we can even do copy it for simplicity. So if assigned index, oh, actually, why I'm doing that? I can do HashSet. I can make it slightly faster. Though in this case, I think it won't matter, but why not? The HashSet is the best data structure for this advent of code. I think I used it in almost every task, so why not here? Contains, if it doesn't contain the index, then we know that we can assign it, right? So let me quickly check one thing. I don't remember if we, yeah, we put new assignment and then we check if it's consistent. So we kind of need to go and see if we got any invalid values. We need to see. So assigned index contains index. Let's do it preemptively. So so for each ticket, we start with valid tickets. So for ticket in tickets iter, if ticket 0 index and unassigned is field to assign. So let's take the rule. So this is not relevant. This is relevant. So we take self rules and we get for unassigned and we unwrap. Oh, sorry, for field to assign, of course. It found string, sure. So that's our rule. And then for, what don't you like? Found usize, sure. And then this is rule we need to match, right? So we need to see if we, oh, here actually I will switch a bit to functional style again, because tickets, I can do iter, and then I can do all, and I can write the conditions that all tickets must satisfy. So ticket, and here satisfied, that rule satisfied. So ticket 0 index equals to what is it? It is let we can do it like that. We can do rule 1, rule 2. So rule 1 contains value, and rule 2 contains value. Right? Right. That probably should be a reference. Yes, it should be a reference here. So now we determined if rule satisfied for each ticket on this position, if for the field we are trying to assign. If that is the case, so if rule is satisfied, what do? We need to essentially call ourselves. We create a new assignment. So assignment will be assignment. We will need to clone it, and we will need to insert into it. We will insert in here will be key, then will be what? It will be the field name. Yeah, it will be field name. So actually, so field name and value will be index. Where is it moved? I'm getting a reference here. Oh, I see. Because we are doing multiple iterations of the cycle, right? So let's do clone. First of all here. And here then we can do... Oh no, we don't need to do clone here. We can do... Because we have multiple iterations here, we need to do a field name clone. That should work, yes. So we got a new assignment, and then we already got new unassigned, so we can call ourselves recursively here, which is self filter index tickets assignment unassigned ticket length. So for now I'm doing nothing here, of course. Assignment found in instruction. Let's call it let mute assignment insert, of course. And then we got assignment. Unassigned it doesn't like because it's also moved, of course. We just clone this stuff. And ticket length as well. Okay, now of course the thing is we need to eventually return it. So we also need to model if we actually get the result, right? Because sometimes we won't get the result. So that will be option then. This will be option 2. So this will be sum. And here, actually, yeah, let's do match. And if sum assignment, I think result as result. Alternatively, none. Actually, that's always will be our result. Let me quickly check again the logic that we have. So if it is consistent, we get solution. If we got solution, then we stop. Otherwise, we continue, right? I think then some assignment. I always forget where to put this in. Don't you like? Expected unit type. Okay. So then we return result, right? I think so. Yeah. We found the solution. We return it. Alternatively, we just break. Now it doesn't like this button on the wrong side. Okay. So this is the thing. With some bindings. Sure. Okay. And then this we should be able to remove something. If we didn't assign anything in the end, we return none. Okay. So why would that work? At least as far as I understand it. Well, because we need to assign, like, first, each field should have an index assigned. So we iterate through all possible indices for each field. We start with the first field, we iterate, and if there is a solution, we should find some assignment that eventually will be correct, starting with this index for all indices. When we do recursively, we have one less index to assign, and if we are on the right track, we will eventually find a second index as well, etc., etc. So if that works, this recursion should eventually return some, and we should terminate with this. If it doesn't work, we will return this, because then we didn't find the solution doesn't exist. Or, of course, eventually, if we get, like, how do we figure out that we found solution? Unassigned becomes empty, and then one of the recursive calls, we return some, then we terminate here. So that's how it works. Now, that should be enough for us to call it. So field to index, valid tickets, assignment. And let's debug it and see what we got. I'm excited. Oh, was wrong excitement. We got none. So something doesn't work. We will need to debug, right? So let's start with just debugging what we got for each recursive call, right? We got tickets. We got assignment. We got unassigned, and we got ticket length. And then we say field name. So what we are trying to assign. And then we say doesn't contain. Rule is satisfied. Tickets for all tickets. Rule contains. Rule contains. Rule is satisfied. Assignment clone. Assignment insert. So new assignment. So that's what I want to track for now. Let's see. Value borrowed here, value moved here. Oops. 102 is here. Oh yeah, of course. So let's try it again. So something happens, but we only execute one. I wonder how. So we get tickets, 3 tickets, all of them are valid, 3, 9, 18, 15, 1, 5, 5, 49. Then we got empty assignment, and then we got unassigned seed row in class, and we got ticket length 3. Okay, input looks correct. Then for class, we find no assignment. Okay, that looks interesting. So let's debug a bit more. So we have rule 1, rule 2. I think those things are copy. So should be all right. And then for each index. Right? So field name we get seed. So that's row. Rule is 0 to 13, 16 to 9. And then we get for first ticket. So index is 0, value is 3. Oh, I'm dumb. I know where my mistake is. I think I wrote and instead of or in my rule. Yep, I did, because it's actually or, of course. Okay. Let's try it again and see. So assignment that we got something. Let's see. Row 0, class 1, seed 2. So the first position must be row, the second position must be class, the third position must be seed. Okay, that makes sense. So let's quickly write a test to verify that. So we say backtracking works, and we just say so that our input, and instead of solve, I will remove this stuff, of course, because you don't need it. And I will just do task parse input. So that will be our task, and then task field to index, where we get tickets being task tickets. So let assignment, and then we just assert that assignment is equal to well, let's do it like that. So assignment for row will be 0. For class 1, for seed 2. So let's check quickly the test runs. Yeah, of course we also need to do, let's do just sums here. So sum input, sure. Task tickets found struct, sure. into a value. And here we need to do, of course, unwrap. Still doesn't like it. What don't you like? Found struct string. Oh, dump. Yeah, I need. Ah, no, I still think this will be references. Yes, so I just need to add reference. Gosh, what don't you like? Expected type usize. Oh, and here we don't need some. Okay. So let's remove this stuff and okay, stuff works, and now we can run it on our input and see what kind of assignment we get, right? So yeah, and we will need, of course, to also solve this thing. So what do you get if you multiply those 6 values together? So we take, we unwrap it, and then assignment keys filter key starts with departure, right? So departure track, departure location, blah blah blah. We collect that departure fields. You can actually even say let mutable result equals to 1 multiply, because we are multiplying, and then we can just say for departure field in this stuff without collect sen, we can do assignment departure field result multiply by this stuff. Move the value, sure. Let's yeah, let's not move it here. Let's move it here, and then we get some box result box new. So for our first part, we should get, what's the value? You can 12, 11 instead. Oh, we cannot really, right? So we just need to do it with the input because we don't have it in our sample input. So let's try it. I'm excited. So of course it fails because option unwrap a field to index doesn't work. How it is possible? Did we go too fast with our solution? Tickets, invalid values. So get valid tickets. Valid tickets. Field itself is valid ticket. Self value matches some rule. Are we doing everything correctly? We are taking input 16. Let's debug our input. Actually, no, I already verified that that works. Field to index. And let's also say solve 2 on this task, just in case. Option on input, of course. And that will be, let's do it none for now and see what it will output, because I'm also trying to see if we are doing something incorrectly maybe there. So we got some 1. Oh yeah, of course, because we don't get anything, right? So that will be some box new 1. But it doesn't fail, so we still have some error in our backtracking. That's weird. It works in sample input, but not on our... Oh, 200, yeah, sure. But not on our actual input. That's so weird. So we really get it here when we do task filter index. Can it be the case that we are doing something dumb? So those valid tickets, maybe we are not filtering out everything, I think. So now that you've identified which tickets contain invalid values, discard those tickets entirely. So for each of the tickets that is in a task, we filter them and only take valid tickets. And is valid ticket is for value in ticket 0 iter if some value matches some rule. If it doesn't match some rule, we return false. Otherwise, we return true. Ticket 0. So if we didn't and value matches some rule, so we get self and we get value where rule 1 contains value if return true. Actually, that can be rewritten a bit simpler, right? So that can be the thing here. Otherwise, we return false. It still looks correct to me. So I guess if we run only the last test fails. Okay, where else? Running one test. Yeah, because of course this is it expects none. But this one works, and this one works. Okay. So apart, I'm not sure. Let's count valid tickets. So valid tickets length, right? And see if what we're doing actually reduces the amount of tickets we get. $190. Oh wow, it's actually more than I thought. So from this we get to 190. Okay. Can it be that we still get some invalid tickets in our input? That would be so complex and to solve. I don't think it's the case. The order is consistent. It is the third field in every ticket, including your ticket. You have the following. Oh my god! I think can it be the case? So when I go here, I go from for index tickets iter all. No, I do it for all. So I only do it for all, and I say every ticket value at 0 contains rule 1 get field name. Field name is fixed. That is interesting. Just for in case I'm doing something dumb, I will clone this stuff here because I'm afraid that I may be polluting my namespace a bit. It still fails, but optional wrap on non-value. I guess we need to see then where we fail. So let's do this. Because I really wonder that happens. And then I can run it again. So it seems we are starting quite well, right? Departure location is 1. I will take us 2. Oh, actually, we can remove the stuff with name index and just have assignment, because I think it will be a bit easier to read. So let's see. So we start with departure station 1. Departure station, this role. I think I know what's the case. I forgot my ticket. I didn't insert my ticket in the thing. I think my algorithm is correct. I think it's, I wonder if we ever backtrack. I'm not sure. I think at some point it just fails completely. And here, of course, it should be continue. It shouldn't be break, right? We just need to try the next value. So that's the first error. Okay, that's, by the way, is not correct, because I need to take my ticket. So your ticket departure field. And then it says, okay, assignment. So departure field index will be departure assignment departure field, then departure field index. So that's the thing. Of course, it doesn't like it. Oh, U64, sure. That we can do. So let's try it again. First continue, and then we see if we need to add our ticket there. Oh, well, now it looks like backtracking running, because it prints a bunch of stuff, and you can see that they are growing and shrinking after it fails with some recursion. So that can run for some time, I guess. Oh, by the way, before I spend too much time on that, you know what I will do? Let's first see if that works. Okay, that still works. Well, it backtracks immediately, so not a problem. Valid tickets. Let's make it so. Let's just push it there so that we will fail a bit faster. We push task your ticket clone. So that's one important thing. And then we can do length. And then I will only print assignment here, but I won't be printing stuff in here, right? Right, I will just remove it for now. Okay. And then I can try to run it. So it still may take quite some time before it runs. I can also even try to run it in release version because it may be significantly faster. So let's see if it terminates. So far it doesn't, but we know that it probably iterates through those options. So now we may have a problem with our performance, right? Another thing, of course, if it even terminates, it should. I don't see a problem with that. So it will continue and then will return none. Yes, and here it will return some. If self field to index. Actually, is it continue? So like if I got, let me check. So if solution do halt, otherwise we continue. Otherwise we continue. Yes, in any case we continue. That makes sense. Oh god, this is so slow. Is it supposed to be so slow? And it runs, and it runs, and it runs. So I wonder how long iteration takes, or if we should actually. By the way, one thing that I may avoid, do I actually need to do cloning here? I think that may be quite slow. So let's see. Right. I wonder if we can try to run it on. You know what I'm thinking about? Just in case if it really will be very slow and we won't be able to optimize it significantly. I will keep one instance running here and I will experiment in another console. So let's do cargo run release. And I will do g16.2 sample 16.2. So that's our one iteration with those rules, right? Very fast. But we got way more stuff happening here. So, and we got like, I think, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 fields. So we need to do 20 assignments. It's quite a lot. And we also, which was also need to check too. I think checking is quite efficient. I'm just also thinking if we have some optimizations that we can derive from this logic. Departure station. I'm also thinking if my solution actually, like if my idea of adding my ticket to the list of tickets there helps. Nearby tickets. Based on the nearby tickets in the above examples, that your ticket. So actually, I don't need to do it. I don't need to do this, I guess. I can rerun it. So, yeah, 190 is the valid tickets number. And then what can we optimize on? I don't see any domain-specific optimization. Can we do AC3 on that? So, well, we kind of do already, right? We remove, at least we remove the rules. So if assign index contains assign index. Oh, I think I know what I can do. So assignment values. I can pass this stuff already, right? And then I don't need to create a new hash set in each iteration. So what is, well, with this stuff running in the background, it's quite different, but for assigned indexes will be hash set of view size, right? So then here we say hash set new. If assigned indexes contain, because then we don't do it preemptively, we only do it here. We do it here, and then we say assigned indexes will be assigned indexes clone, and we do assigned indexes insert index. So let's see if it will help us. This stuff is still running. Oops, not what I wanted to do, of course. I wanted to do D16 sample 16 to this stuff. So it doesn't seem to be that different. Well, oh, we're also solving it here. Okay, stop. No. That will be too slow. So I'm thinking about measuring how it will perform if I have samples 3. So I will just put, because I need a more representative thing, right? So I will do sample 16.3 where, oh, no, I don't want a folder. I want to just have a file. And here I can take this stuff and I can just like take away less tickets here. So I will take like first until 100. It should be already faster, but I should get more realistic example. And then I can run against it, so I will get a bit more honest comparison. So here we see that we arrive at something. Well, every time I think they're different. So departure track 6, departure track 5, because obviously we don't have enough tickets to constrain it. So it's around, I say between 400 and 500 microseconds. This is with my assignment thing. I will just commit it, and then I will try to git add source, git status, git commit, day16 part 1, and first attempt at part 2. So then, actually, just for fun, let's try to run it. Well, I guess it won't really work. But while it runs, we can see if we actually improved our performance, right? With this assignment stuff. So I will just go back to my previous logic and see if it helped anything. Well, till there, I guess. Stop. And then I can execute it again. So actually, I think it doesn't really help, right? Well, there is a lot of variation, but I think Well, one thing it does for sure, it makes my code nicer, and I think that it doesn't really matter. Git checkout source t16. Cool. Yeah, part 1 was comparatively easy for me, Thomas. Part 2, I think I have correct algorithm, but it runs too slowly, so it's still running. For smaller inputs, though, it works. And I was right. It was about constraint satisfaction this time. At least that's what I got. Okay, actually, I got same. I think it does help slightly, but it's really tough to say without... yeah, this is the checked out version, right? Ah, no, maybe not. It's really hard to say without having proper benchmarking here, but I think it's slightly better. There's also a very big variation, of course, in how it works depending on the input and depending on the... Okay, sure. Depending on how fast we converge to the solution. So you can see that our numbers vary from 600 something to 300 something, which is pretty significant difference, I would say. Now this thing is still running. Okay, do we do anything more that is super inefficient here? So we're also doing a lot of recursion, which is interesting. We can try to do an iterative solution. I guess it should be pretty straightforward. Contains true is satisfied. Let's also see if we can do one thing here. So let's extract this logic to make it a bit more compact so we can see it a bit better. Here we say then take reference to self. Do we oh well. It would be a bad idea here then, because then we will need to pass additional reference every time. For this rule, for this thing, assigned index contains index rule is satisfied. I wonder if this is really so if I take a bit more tickets, so starting from 100 and I take say till 150, 895, yep. So if I do it like that, how much slower will I be, I wonder? Because, okay, so we can copy this stuff. Because I really wonder if we need all of them. Oh, okay, not what I want to do. I need to copy this thing. Eh? What the hell is happening? Okay, copying is broken. Okay, let's see. We are still very fast. What makes us so slow then? But yeah, it's still not stable. So we went to 150. If we go to 180, 466, yes. Oh. So day 16.3, oh, 2, sample 16.3. Let's try and see. Arrival location, departure location, arrival track 13, arrival track 14. So it's still not unique, but it's still very, very, very fast. I guess because we really 180. Okay, is it possible that we get how many valid tickets? It says 125. And here we got 180 minus 26. So I guess we started to get invalid tickets, right? Let's try to add a bit more. So let's go to 220. 291. I'm just also thinking that I may arrive at something where I can cheat a bit and precede my input. So like if I can figure out at least one, I can already reduce complexity of the task a lot. So you see our timing is now bigger, which is a good sign because it means that it now goes through multiple options. Departure station 12. Departure station. I think I arrived at input. Departure station. Oh no, departure station 3, departure station 18, departure station, oh, price 16, road 9, price 15, price 15. Hee. I'm also thinking that I may be going through the same assignments in different branches of recursion, right? So once I determined that some rule for some field is broken, for some particular assignment, I shouldn't try the same assignment again. Which means, oh, I know what I can do. I can do like a Tabu list. So I can mix backtracking with kind of like Tabu search, where I add those rules, where I say, okay, you shouldn't try to look at that again. So let's try to do it. We can call it excluded. So we got tickets, we got assignment, we got assigned indices, we got unassigned, and we got ticket length. And we can then say excluded assignment or Tabu assignments, which would be a hash map from well, string to a vector to hash set of use sizes. You see, so like for each of the fields, we will maintain this hash set where we know, okay, that won't work at all. And then we can just skip them. We can skip trying them, and we can skip like going into multiple branches of recursion based on that. Search for the term Tabu search in Google to get a better understanding of this idea. But this is one of the heuristic methods of local search that you can mix with constraint satisfaction solution algorithms. So here then, what do I need to do? When do I determine if assigned indices contain? So if rule is satisfied, if rule is satisfied to do this, but then I can also do else. Tabu assignment. And this will be a mutable reference to one shared map. So here, Tabu assignments will be a hash map new mute. Let's even add it here. And we just pass it here. So if we know that rule is not satisfied, we know that we cannot assign this index for this field name. So entry for field name or default, the default, or insert, I mean, which will be HashSet new. That will be our Tabu indices. Indices, I mean, Tabu indices. And here we just insert our index, really. That's it. I guess, don't you like? To index inner. Ticket lengths. Tabu assignments. So that's it. We excluded thing. So let's see if that will help us. Oh yeah, something is broken. Hash map. Oh yeah, of course, we need to pass actually immutable reference. So, and let's see if our thing is still solved here. Okay, it seems we didn't break our first test. Let's try to do the second thing then. So cargo run release, and I'm so hopeful right now. Oh yeah, actually I forgot to use this in, right? I fill it in, but I don't use it. So if assigned index and excluded, we just say Tabu assignments get field name. Unwrap or, right? Found struct HashSet. So excluded. We can of course also pass sentinel and then check. So and here we just say if signed indices contains or, and excluded doesn't contain index either. So that's our additional rule, right? Here, what don't you like? Well, get field name. Well, so excluded is none, or I will just do it like really ugly way, but it doesn't matter. So, oh, it doesn't like it anymore. Still support as mutable. Oh, field name. I will just do clone here, or unwrap or, and I'll just do then HashSet new, right? Dumb, but why don't I like it? Come on. Nearly contains. Of course, no, not unwrap. So collection found struct. Why does it want a reference? If I remove this thing, will it be happy? So excluded will be option HashSet, of course. Well, excluded. Then we do excluded option. Can I do unwrap O here now? Oops. I think so. Yes, finally. Ownership, borrow checker defeated. Let's see if this stuff still works. So I may have made things just worse, by the way. That's also absolutely possible. But let's see if I did. This thing's still running, so we have a lot of time to try this stuff out. It should, in principle, prune our recursion quite significantly. D16.2. Well, still running. Oh, well, we actually can see if it improves things first. So sample 16.3. Oh, wow, it improves things by a lot. So we had like 1 second, right, for previous versions. Like 500. 400. Oh no, 400, 700, 600. Let's see if I'm doing it correctly. So yeah, let's do git stash and run it. You see, git is very useful for trying this kind of stuff quickly. Oops, not what I want to do, of course. Sample 16.3. So part 2, what I'm doing. So 400, 300, 500, 500, 500, 500, 500, 4, 3, 7, 4, 3. Okay. I think we made things worse. Oh, well. I also made my sampler address, so stash inputs. I think I can do it like that. Git stash. Pass back. Minus, I guess. Yes. So now we should have only changed code, but no change file. Yes. Okay. Cool. Let's run release and see. I will be streaming till 11. If at 11 it still is not solved, then I will finish for today. But I really hope that we will be able to finish it. I think we closed. So, okay, it became slightly better. So now I will just stash my sources and try the larger input. And let's make it even a bit larger still. So we got 220. Overall we have 263. Let's go here. So let's take this 855, right? I want to go to 240 actually. So that will be my input. what do we get? We get our input. We can try to run it now again without changing the code. So 1 millisecond, 2 milliseconds, 700. Ooh, takes longer time, you see? I have another idea that I can try if this exclude thing doesn't work. I can try to run it in multiple processes with randomized state. Then we can get lucky. 21 seconds, 2 seconds. You can see how big the difference is, right? Like depending on what we start with, it can be 2 milliseconds, 12, 900, 700 microseconds, 1 millisecond, 9 milliseconds, 263 milliseconds, 1 millisecond. Okay. Now, copy it just in case. So we got still 240. Okay, this is splendid. And now our exclude thing is back. So we can then do cargo run release, right? Okay. Of course. Part 2. 1 second, 500, 600, 2, 6. 6, 501. Honestly, I think it made things worse, which is a bit weird because we are pruning stuff. But I guess there is also such a big variation right now in terms of runtime. At least we know that it actually backtracks and it finds stuff. Okay, wow, okay. While this thing is running, oh yeah, typically you also need to limit the size of Tabu stuff. So you know what? I will do, I will commit it for history, but I will git add inputs, git add source, git status, Tabu attempt, because the thing is, it also at some point starts to just grow and it can become more problematic. I will remove it for now. I think that didn't work and I will try to do multiple threads. So Tabu was, yeah, Tabu was there. So, and here we don't need to do that anymore. And here we don't need to check it anymore. And then we need to do threads. So we need to run multiple threads, and the moment where we get something, we need to terminate. So let's quickly look up the docs. By the way, yeah, it's still running. I guess we can, by the way, give up on this attempt and try to run it again. Because as you have seen, sometimes just running it multiple times, I forgot what I'm doing. I'm doing thread. Actually, we can just try to run it multiple times and see, because maybe we will get lucky. We only need it to succeed once, in principle, to solve the task, right? You don't need to do it like... Okay. Or we can actually also run it in multiple terminals, which also makes sense. So this is like poor guy's threading right now. I'm just running it manually in multiple terminals. Hopefully that one of them will return the result I need. I don't think I need to change my algorithm because I think that's the algorithm we actually supposed to use. It's more about the fact that, as typical with those problems, you don't actually know, right? It's kind of randomized. And in the worst case scenario, it never finishes. But what can we do? So I'm just quickly also checking that this stuff works. Yeah. So we have 5 attempts now. We're running it essentially in 8 threads. In 5 threads. Manually. Which is a bit funny, but okay. And while it runs, we will try to make it multi-threaded here. Actually, I can just do thread. So I will need threads and I will need channels, right? So those two things. And here I will just... Oh, wow, that was quick. Yeah, part 2 turned out to be more interesting than I thought. I don't know, maybe my code is also so unoptimal that something is really wrong with it. I don't know. Yeah, I touch it so rarely. Like, I don't typically do multi-threaded stuff because most I use Rust for speeding up like one little part of something where it doesn't make sense. So I will be struggling right now too. But at least it's a funny thing to try. And I think I will try for like 22 more minutes. And then if I don't succeed, I will give up for today. But yeah, I think it's enough time to try the threading solution. It wouldn't be enough time to try a completely different algorithm. So of course, another thing that we could have tried is mean conflicts algorithm. So we can try mean conflicts, meaning that you need to select the assignments that minimizes conflicts, but that I won't be able to write in 20 minutes for this task. So I will create actually MPCS thingy, let multi-producer, single consumer. Okay, so that should work. So for let's create a channel. Block the colon strategy. Will block until this message is available. Okay. So we will get sender. Let's return it in this order. I always forget because they use sender, receiver. Yes. Now, thread spawn, sender, send, unwrap. So for yeah, you can try mean conflicts algorithm if you want, because I'm trying backtracking. It doesn't seem to be working. So I can give you this hint. Or maybe there is some other approach, because I immediately, for me, it's constraint satisfaction problem. So I'm trying the constraint satisfaction algorithms for that. And backtracking is typically the thing that is most general. And I think even last year we also had a problem for backtracking, but I don't recall if I tried to solve it. But yeah, so sender receiver, and then we have, let's say we have let threads count, and we say, I don't know. I think let's try 8 and say 4. Just join. I don't even need join handles, right? But well, I can still have them just for completeness sake, and I will do 0 to 8, and I will do it to iter, and then I can do map, and here I will have ID. Yeah, true. That's also an interesting approach. For me, it would have been so weird not to try something that I already discussed on my channel and that I researched for quite some bit to do those videos. So kind of makes sense. Actually, yeah, let's do a quick survey. Okay, none of them has terminated. Index. We completely ignore it because we don't care. We just create a thread. Where we have, where we do what? Valid tickets, valid. So we clone stuff that we need in this thread. Actually, I can even do it like that before I send it, right? Yes. And then spawn. I can tx send. I can do this. Fill to index valid tickets unwrap. Can I share a reference? I think I can share a reference to valid tickets. I think I don't need to clone it. And assignment if. And I don't want to fail if one of those threads fails, so I will just do much here. And then I can do right. I can clone this stuff, and here I can do sender, send, and here I can send my assignment. And otherwise, I can just do nothing. Yeah, like that. Result, send error. And I can also, oops, do debug assignment. Then sender, send. So like that. What don't you like? Sync cannot be shared with is not implemented for sender hash map string is size required as input for it appears within the type task valid tickets sender. Okay, let's see if we can try to get Is this error more readable? So it says this cannot be shared between threads safely. Collection hash map string usize cannot be required by this. Do I have some reference inside this thing? Sender collection hash map string. I don't think so. Send required. The trade sync is not implemented for sender. Required because of the required implementation sent for reference to sender. Collection hash map. Required because it appears within the type. So I have this reference here and it doesn't like it. So here I guess I need to do move. Valid tickets, of course. Tickets. Can I do it like that? To avoid excessive copying? No. Okay, well, I can always just clone them. Why not? Clone. So I'll just also debug this stuff and then be use. Well, I won't be using it for now at least. Join handles, of course, don't care. And then receiver receive. So here I'm implementing. Yes, true. It is, I guess, one of the most. Yeah, I think it's actually is the most interesting puzzle. I agree. So yeah, I'm doing something that is not typical here because I first receive and then I will try to join in the very end because I need to report. Or I won't even try to join, I guess. I will just receive stuff here. And then just match this. So if I got result, or actually I got assignment, then what I can do, I can do this. Otherwise, I will debug my error and I'll just turn on. And join handles I don't actually use, but it doesn't matter. And here, of course, I need to do thread counts. Okay, that's the multi-threaded solution, I think. Whoa, we solved it. We solved it in 454 seconds. Oh God, that was long, but you see, my idea was just running it. Woo! Oh man, we did solve it. Okay, that was funny. I still want to see if my multi-threaded thing will work, but that looks really cool. Oh man. I guess for test we can just precede it, so it doesn't take so long. I will just copy it here. And what is our test output? This is our test output, right? But yeah, 454 seconds. Oh man. Thank you, man. Oh God. And actually, so this was one that terminated, and another terminated is in 458 seconds. Number, oops. What did I do? I accidentally pressed on 0, I guess. Yes, so 454, 458, and the number is the same. So your solution is unique. And others are still running. Okay, stop, 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 stop. Be prepared that you will need to spend a bit more time on this. But I really wonder how you will approach it as well. I think it's really, you can take multiple roads here for sure. Let's also do some, just to show that we are doing something useful here. Let's do this. So we will do debug index, so we know where we are. And let's just print it here as well, right? I still think I'm probably doing something so slow in my theme because I don't think this should be running for so long, honestly. I think that's probably just, oh, yes. So I guess I'll just do it here to make sure that I'm actually running multiple things at the same time. So it builds. I don't have anything more running. No, I don't. Okay, that's splendid. So let's try. What? Why don't I get the nice... Is it even printed at the same stop? So threads count into map. It should be printed here, right? It cannot be the case that this stuff is not printed. I wonder also while that compiles. Yeah, it looks interesting. This is like, I guess, an island, airport. Cool. It doesn't print stuff. Did it get the same output? Because I really wonder now if we actually run in multiple threads. Can we make it look like that then? And can we then do what I wanted to do here? So saying thread index. And then here, I don't care. Actually, I can also do unwrap or default. Assignment. What will be default actually? It will be like result. Unwrap or terminate. I really don't want to fail this thing. So that will be correct, I guess. And then I don't need to do debug here. I can do this. Okay. So slightly nicer code. Yeah, I have 8 threads of execution because of hyperthreading. I think it's only 4 cores. What the hell? Why do I actually do it correctly? I'm just thinking, why doesn't it print stuff? It should print things here. So, no, what? Simplified print line. Starting thread index. No. Can we move it past here? Okay, if printing doesn't work, I will try to see in top if I'm actually running this stuff. So I guess let's try it again. Actually, sure. Let's not 9. Could be how to call it. I don't want C# dependencies. I don't need. Oh god. Okay. I hope I won't have just to make sure that this doesn't happen. I will switch off the sound on Spotify because yeah, that's one of the problems of having non-standard keyboard setting, because I'm not sure that if I press F5, what will happen. Or actually, I can try this. So, okay. Oh, you know what? I'll just do terminal. That will be easy because I now understand what happened the last time when my camera broke, because it was probably this debugging command in Visual Studio. I need to disable that. I never use debugger. I think I never once in my life used debugger in Visual Studio Code. So yes, I need now. Can I click on that actually? Oh, I can. Oh, okay. I can click on that stuff. Terminate. So tree. Eh? I should be able to click on you. Okay. I need to do it here. Terminal. Terminal. Splendid. Top. Click. AUG 2020. Zero processor it uses. A. Okay. And no additional thread of execution. Just in case, I will also say let's make sure that we join them. I'm not sure if it does some kind of additional logic, but okay, we solved the task. That's the main thing. Multi-threading stuff doesn't seem to work as nice as I thought it will. So handle in join handles into iter handle. Is it like thread join? Waits for the associated. The completion synchronizes with this function returns performed by this thread are ordered before all operations into. Can I like kill it? Thread to the underlying thread. Okay, thread, and then I can kill it. I just need to kill this thing. So clone continue debug into match name reference to owned unparked. I cannot kill a thread. How to kill a thread? Keywords. name unpark. ID. Thread ID SU64. There is no way to kill a thread in Rust. What the hell? That doesn't make much sense. Yeah, so I can join them, but I cannot kill them. What? That doesn't make any goddamn sense. Stack size current panicking. Do for some time. Okay, I don't see a nice way to actually terminate the thread. That sounds really dumb. But apparently that's a thing. Okay, and I also don't believe that it even executes properly. Which is interesting. So set is non-blocking. It will never block the current thread. Okay. Send expect thread spawn. Receive. Oh. Well, no, stop. That should work. Spawn. I'm not sure if I blocked myself here. So like, but in principle, receive should wait. Those should be already spawned, and then everything should be alright. I don't know. Maybe one thing that I can try is do this, because I know that I will need to wait. I don't know. Okay, this looks super weird, because I will just try to yield in all of those. Oh, of course, I need to do this first. Okay, if that doesn't work, I'm finishing the stream for today after trying that one last time. We didn't need to implement multithreading, we could just run stuff. Yeah, nothing happens. Okay, I don't understand why. I will investigate it after the stream, I guess. In any case, backtracking in multiple with multiple attempts did work in the end. We didn't solve the thing. I will just in case put here an ignore tag so I don't run it when I run my test accidentally. Otherwise, was very funny task. I really liked it. I think so far it was the funniest task. I'm a bit surprised that it took so long to find the solution. I guess I'm either doing something very inefficiently or there is some kind of trick that allows to make it faster. But overall, it worked. We solved it. It required a bit of hacking with running multiple terminals at the same time. But what can you do? Thank you for watching. I think it was the most exciting day so far, and I see you in a couple of days.